Hello, everybody. Welcome. This is now talk number 2 in the lecture series. So today we are going to be talking about risks from learned optimization, which is based on a paper that I wrote with some other people. I wrote it also partly while I was at OpenAI, which is why you're going to see some OpenAI branding on some of these slides, because this talk is from them. But yeah, it's about this paper. OK, so let's just get started. So yeah, so what are we talking about here? So just return again back, very quickly to, we talked about this before. This is our sort of stereotypical machine learning algorithm. What is it that machine learning does? Now, we talked a bunch last time about this basic process of searching over possible parameterizations of some function to find values of those parameters that result in the function having some particular desired behavior on some data set. And one of the things that I really tried to emphasize last time that is really important in thinking about this is it's hard to think about. It's actually really difficult to understand exactly what sort of function, exactly what sort of parameters, what algorithm you're going to end up implementing when you do this procedure. You get something like the simplest algorithm that fits the data, but exactly what that means is complicated, and we don't exactly understand. OK, and so because of this, it's difficult to understand what's going to happen. We don't always actually understand what this process is going to do. It's tempting, and in fact, people will make use of abstractions, ways of trying to understand what this is doing that don't literally go through the actual process of what it's doing, but allow us to sort of abstract away and understand something in theory that describes a way of thinking about it. And so a very common abstraction that people use in thinking about this is what I call the does the right thing abstraction. So the idea of the does the right thing abstraction is that, well, what the procedure that we did here was we selected the parameters to minimize the loss over the data distribution, right? The way that we actually selected this, the way that gradient descent was structured, the way that it actually worked, was that it did this big search and it found parameters that had this property, right? And so we can sort of imagine, in some sense, that well, if we want to try to understand what that function will do, what the algorithm will do on new data, we can sort of imagine that in some sense, our model is trying to minimize the loss, that it is sort of actually attempting to do the thing which would result in the loss being minimized even when it sees new data points. And this is a really useful and helpful abstraction. There are a lot of situations where it's very difficult to understand what exactly it is that our model is doing. But by using this abstraction, we can make some pretty good guesses. If I trained a model in an environment where there was a gold coin and I trained the model to try to get the gold coins, it's a pretty good guess that if I put it in an environment where the environment is slightly different, I've changed some of the parameters, but there are still gold coins, it might still want to try to get the gold coins. That's often what is going to happen. And so it's not a bad abstraction. It's often very useful for helping us understand what's happening. But it's not true, right? It doesn't actually describe the process of machine learning, right? The thing that we did was not build a model whose goal was to minimize the loss. The thing that we actually did was search over a bunch of parameters to find some set of parameters which in fact had the property that they resulted in the loss being low, that they did the right thing on the training distribution. And so the abstraction is not in general true. And in many cases, what that means is it's going to leak. There's going to be some situations where the abstraction doesn't hold. OK. And so I want to talk about the sort of purpose of this talk. The thing that we're going to be talking about today is a particular instance in which that abstraction doesn't hold, a particular instance in which it fails to work. And so to understand that particular instance that we're going to be talking about, we're going to introduce a concept, which is the concept of an optimizer. So what is an optimizer? So we're going to say that a system is an optimizer if it is internally searching through some space according to some goal. It wants to find something in a space that has some property. So it has some sort of representation of an objective of something that it wants to find in that space, and it's looking in that space to try to find something with that property. OK, so examples of things that are optimizers. So gradient descent is an optimizer in the same way that we've talked about and described, where gradient descent is searching through the space of possible parameterizations of a function to find parameterizations which in fact result in good performance on the loss. Other things that are optimizers, something like minimax. which is just like a simple like chess playing or any game algorithm where it sort of searches for the best move n steps ahead, assuming that the opponent makes the move that is worse for you. Okay, and humans are not always optimizers, but sometimes we behave as optimizers. There's lots of cases where we have some goal, some strategy, something we want to accomplish in the world, and we try to look for strategies that actually accomplish that goal well. And so we search for possible actions that do a good job at accomplishing that goal. Yeah, question?
Yeah, so gradient descent is this local thing. Minimax and humans, they can search over long time spans. How relevant do you think this is to the definition of optimizers?
Yeah, so it's a really good question. It's definitely, in fact, the case that in many cases, gradient descent, or in many cases, you will have optimizers like gradient descent, for example, that is like local. It's just looking at each individual step, and it's not doing some sort of long-term optimization. And sometimes you'll have long-term optimizers like humans that have some really long-term goal. For the purposes of right now, what we're going to start with, trying to understand. At the beginning of this talk, I'm mostly going to ignore that distinction. We're going to be looking both at, optimizers with these sort of, short-term horizons and long-term horizons. We're even going to, think about optimizers that have an objective that is about the world, or optimizers that have an objective that isn't even about the world at all, right? That's maybe just they look for an action which has the property that, it has, some fixed property. Like, they just want to output, something which is as close to some fixed value as possible. They're not necessarily trying to optimize something over the world. So we're just looking for optimizers in general. Later on, near the end of this talk, we're going to sort of return and be like, okay, what happens if your optimizer has particular properties, like, like it's long term, and why might that happen? But right now, we're not talking about that. Yeah, question.
Abraham Dembski has this sort of distinction between selection and control, and I guess these are two types of optimizers. Selection being something which seems something similar to what you've written, which is that it's searching over some search space and looking for candidate solutions that it can stash it in search space and measure the performance or something. That it just does like an argmax over this. And then control is something that it's a bit more greedy and like it knows that like it can instantiate solutions in the candidate solutions in the world, and it needs to act as such. So do you think that sort of distinction has some relation here?
Yeah, so that's a really good question. I guess a couple of things that I will say. So I think that just to start with, so I think it is an interesting distinction and one that can often, matter, this sort of distinction between selection and control. For our purposes, I'm mostly not going to make the distinction. I think I would sort of analogize this distinction to one of the distinctions we talked about last time, which is just sort of the distinction between something like supervised learning and reinforcement learning. Where in reinforcement learning, instead of searching over, a sort of function that, results in, a really good, labeling of, classes on this particular data set, you're searching for a general policy which generally results in good things on this environment when it's deployed. And so in the same sense, you can sort of think of the control as, being, searching for a policy which is able to control some environment effectively, whereas, that is sort of different from just like searching for a particular element in a space. But I'm going to, mostly elide that distinction and be like, well, okay, they're basically both doing, some search over some space. They're trying to find some, something with some objective. Even the control is still sort of doing a search. It's just sort of, searching for good policies, for good actions rather than, just like a good element in some space. Yeah. Okay. More questions?
Yeah, I was just wondering. I was wondering about like whether you consider efficient markets as optimizers in a sense. Like it seems like maybe they can't in fact do this search for like the most like they can't necessarily pull out the pathway to the efficient outcome before they get there if there's like too many actors or something. But they can in fact reach the frontier.
Yeah. So I think that we're not going to just imagine that an optimizer has to be like perfect. It doesn't have to always be really good at finding the best possible element in the space. It's just anything that's trying to do search over space according to some objective. And so in that sense, I think markets in many cases can behave as optimizers. It's not like our stereotypical example here, but you could imagine a case where even you ended up with a model that was internally acting like a market. It's a little bit of a weird case, but you could imagine it. And that maybe that's a little bit of a hint of where we're going is we're going to be looking at situations where we have models like this. One thing that maybe I'll point out very briefly also is just the negative examples here, right? So I mentioned models. If we just randomly initialize a neural network, it's not going to be doing one of these things, right? It's just some random parameterization that results in a function that is just doing not doing some coherent, simple sort of algorithm that could be described as something like optimization. What we'll see, though, what we're going to be talking about is the situation where maybe after I train a network a bunch, I do end up with something that's well described as an optimizer. And of course, the reason for this would be the same reason that we talked about last time, which is just that in general, when we train these sorts of networks, we find these sort of simple, structurally simple algorithms. And so this sort of thing that we're describing here, this idea of optimization, of search, might be the sort of thing that is this sort of structurally simple algorithm. That's at least the hypothesis we're going to explore. Other things that are not optimizers, bottle caps is sort of a classic example here, where the idea is that we as humans optimize bottle caps to be really good at keeping water in a bottle, but that doesn't make the bottle cap an optimizer, right? So I want to distinguish between the case where something was optimized over, right? Like any neural network, if I train it, is going to be optimized over by gradient descent, right? But it's not necessarily itself going to be running some optimization algorithm like this. And so we really want to distinguish between that situation. So we're really thinking about things that are themselves optimizers, not bottle caps that have been optimized over by some other optimizer. Yeah. OK, more questions.
So if I take a simpler example, does that mean like an algorithm that, well, a function that outputs the maximum item of a list, would that be considered an optimizer because it is searching across a search space for an internally represented objective?
Yeah, it's a pretty simple optimizer. I think it's not sort of the canonical example we're going to be talking about. But you could imagine that that's sort of at least doing some sort of search. What it's not doing is it's not doing a search over a very large space, and it's not doing, but it's still, doing some sort of like, optimization. And so, you could describe it as doing something like that. It's not mostly what we're going to be talking about. It's sort of an edge case. Yeah, question?
I'm still confused by what you mean by internally searching for some search space, especially if we apply it to gradient descent, for example, which you count as an optimizer. What shall I be thinking about when I'm thinking about the internals of gradient descent?
Yeah, that's a good question. So gradient descent is searching over a space, right, of parameterizations. I guess it's a little bit, what does internal mean? I think, for our purposes, the sort of thing that we're going to be caring about is we're going to be sort of internal to the model, because we're going to be looking at situations where we have an optimizer that is sort of contained entirely within the function that you've learned. You sort of learned an optimizer function. So maybe internal isn't a good word to describe any optimization, because it's a little bit unclear what counts as the internals of gradient descent. I agree, and what counts as the externals. I think that's not super a relevant distinction that we're going to be caring about that much. You can imagine a situation where like if I had a process and what it did was like first it generated a parameterization and then it did a bunch of search over that parameterization, then the algorithm which did that, which first parameterized some function and then search over those parameters, would be an optimizer. If I count that whole thing as one, I draw a big circle around that and I'm like anything internal to this, well clearly internally there's an optimization happening. It has some space of parameterizations and it does a search over it. I think it's not super important where we draw that distinction. And I think that one thing that is sort of relevant is that in many cases, exactly where you should be drawing that distinction with like, models can change because, our notion of like what things count as part of the model and what things are sort of external is a little bit unclear. Like, you might imagine a situation where like the sort of model on its own is an optimizer, but if you give it a bunch of time to think or you give it the ability to interact with some, memory or something, then maybe it sort of becomes an optimizer. I think that, we're sort of going to be including that in what we're talking about, situations where, if you can draw some boundary around it and be like, look, this is my AI, and inside of this boundary, it's doing some optimization, then that's what we care about, because we want to find situations where, you're deploying some system and that system is doing optimization. We want to make sure that optimization is the right sort of optimization. Question?
What if I put a ball in a valley and under its own weight, it rolls down to find some local minimum point in the valley? Is the ball an optimizer, or how would you draw a boundary? What's the optimizer?
Yeah, that's a good question. I guess in some sense, maybe we could say that like physics is doing an optimization there, but the ball is not. I think that it's another sort of one of those tricky edge cases that we're like mostly not going to imagine. I think that like if you had a network and internally the way that the network did things was like it simulated a physics environment where like it like tried to had a bunch of valleys and then it put a ball somewhere and tried to see where the ball would land up and like use that as part of its computation, I would be like, yeah, okay, that's doing some optimization, right? Like it requires an optimization to be able to understand how to solve these sorts of physics problems. So for that purposes, we could say it was doing some optimization. The literal ball itself, is that an optimizer? I don't know. I mean, no, I sort of want to say no, but it also doesn't matter that much because we're not really going to be like, the point of this is not to have like some end all be all notion of what an optimizer is. We're going to be using this notion to talk about a very specific situation where you can have sort of optimizers in your sort of neural network. And so, the sort of more general philosophical questions, I think they can be interesting and relevant, but I'm mostly not going to be engaging with them. Yeah, more questions.
So if I guess if gradient descent is considered an optimizer, is natural selection also considered an optimizer?
Yes, that one is definitely yes. And we're going to be talking a little bit more later in the talk about that particular example of an optimizer. OK, I think hopefully we have some clarity now on what an optimizer is. So we'll keep going. So I've mentioned this now a bunch. But the thing that we're trying to do, the sort of place we're trying to get to, is a situation where we have a sort of model, and that model is itself, internally in some sense, running some optimization algorithm. And so there are a lot of cases where you can have a model that's running an optimization algorithm. In particular, we're interested in the situation where we have a gradient descent process that is searching over some very large, parameterized function. And it's not necessarily, searching only over functions that are optimizers, but it's searching over a large enough space of algorithms that some of those algorithms, especially maybe some of these sort of structurally simple algorithms, might be running some sort of optimization style process. In that case, we'll say the situation where you do end up with an optimizer that, that is what the algorithm is that you found that is implementing, we're going to call it a Mesa optimizer. So this is a little bit of a weird terminology, but the basic idea is that Mesa is sort of the opposite of meta. It's like a Greek sort of prefix. And so you can think about, oftentimes we'll talk about like meta optimization, where a sort of meta optimizer is an optimizer that is optimizing over optimizers. And oftentimes we'll do this explicitly, right? So you can have cases where you just construct a parameterization, right, of some space where all possible parameterizations implement some optimizer. But that's not what we do generally in machine learning, right? Like many of the parameterizations don't implement an optimizer. They're just sort of general parameterizations of almost any possible simple algorithm. But some of those parameterizations might be an optimizer. If gradient descent finds a parameterization that does implement an optimizer, then once it's done that, it is effectively a meta optimizer, right? Because it is now searching over the space of optimizers. And so because this sort of happens emergently, we're going to call the sort of case where you're sort of one level below in the sort of meta optimization hierarchy, means you're a Mesa optimizer, right? So we'll call gradient descent is sort of the base optimizer. And if it is the case that gradient descent is sort of in a situation where it is optimizing over another optimizer, then that other optimizer is sort of a Mesa optimizer. It is one meta level below in the sort of optimization hierarchy relative to gradient descent. So these are the sort of terms that we're going to be using. We're going to say that your gradient descent process that is doing some search over some large space of parameterized functions is a base optimizer. And in the situation where the particular algorithm, the particular parameterization that gradient descent finds is well described as an optimizer, then we're going to call that system a Mesa optimizer. And importantly, this is sort of the whole model. It's just you have a model, and if that model is doing some optimization, then we're going to call that model a Mesa optimizer. OK, questions?
So since earlier you said that natural selection was an optimizer, does that make humans examples of Mesa optimizers with respect to natural selection?
Yeah, so this is one of those classic examples that people often like. I think it can be quite helpful, and I think it absolutely is the sort of thing that is reasonable to describe what's going on here. But it's not an example I want to focus on because I really want to be focused on machine learning. So we'll come back to that example later. You can sort of keep it in the back of your mind. But right now, I think it's a little bit tricky as an example because it's a little bit non-central. There are some things about it that are sort of different. I mean, there's a bunch of things that are different about natural selection that are different about humans. From ways in which AIs might be structured. And so we will be talking about that example, but I don't want to focus on it too much.
I also want to just try and understand whether you could be a base optimizer and a Mesa optimizer at the same time, because you said natural selection can be found as a base optimizer, and then you've got humans who can also be optimizers. But then you just now said that they can also be Mesa optimizers. So are they both at the same time? Or
Yeah.
more concretely talked about neural nets, right? We have stochastic gradient descent as like, say, a base optimizer. We find some optimization algorithm internally, let's say Minimax, and Joel already also said like, Minimax would be an optimizer, so it could be a base and a base optimizer.
Yeah, absolutely. These are all relative terms. So in the same sense that like, I could be an yeah, you could be meta relative to something else or Mesa relative to another thing. If I have like a stack of 10 optimizers, and each one is optimizing the next level down, then like, pick any one of the 10 to be your base, and then everything above it would be like, meta, then meta, meta, and everything above it would be Mesa, and then Mesa, Mesa, right? So this is all relative terminology, right? And so we're saying that relative to gradient descent as the base optimizer, if you were one level below that and you were another optimizer, then you would be a Mesa optimizer, right? And so this is not like absolute terminology. The only like absolute term here is optimizer, right? Where like things are optimizers or are not optimizers. But like, is a thing a Mesa optimizer? Well, it just depends relative to what base optimizer, right? Cool. Yeah, question.
Where did the name Mesa come from?
It's just Greek. It's like was picked to be sort of opposite to meta in terms of like Greek prefixes. I don't speak Greek, and so I don't really know. I have had some people who do speak Greek that claim that it's not a great match, and other people that say no, it probably is the best match. I don't know. Whatever. It's what we're stuck with. There wasn't like when we wanted this, there wasn't like a really standard Greek prefix that corresponded to the opposite of meta. We did some searching, and we found Mesa was sort of like reasonably approximate to what we wanted, and it's got a nice ring to it. So it's what we're going with. But whether it actually is like correct in like a Greek sense, I don't know. Whatever. It doesn't matter that much. Just imagine that it is. Okay. Cool. All right. Let's keep going. Okay. So I talked about this very briefly. So like things that are wrong. So we're not talking about a Mesa optimizer as a subsystem. We're just talking about it as like a whole model, right? So we're really going to be focusing on the specific situation where you have gradient descent is your base optimizer, and then gradient descent finds a parameterization of a function, some algorithm, some a neural network or whatever that is doing some search internally. And if there is search happening, if there is optimization happening inside of your model, your network, your AI, then we're going to call that a Mesa optimizer. Okay, we're not going to be sort of identifying particular parts of the algorithm. We're just talking about the whole thing. Okay, great. And then I talked about this also a little bit, but we're sort of this is very related to this general concept of meta learning. And so one way you can sort of describe what's happening here is sort of emergent meta learning, and this is often how this sort of stuff has been described in other places in the literature, where the idea is that you're in a situation where you didn't think you were doing meta learning, you just thought you were doing normal optimization over some space, but it turned out that some of the things in that space that you were searching over were themselves doing optimization. And so now you're in the business of meta learning, even though you sort of didn't imagine originally that you were. And so in that sense, we can sort of also refer to this, this sort of Mesa optimization as a situation where you have emergent meta learning. Okay. All right, so returning back to what we were talking about earlier, we have this does the right thing abstraction, right? And we're sort of concerned about situations where this does the right thing abstraction might be wrong. And so first let's ask, what does the does the right thing abstraction say in the case of Mesa optimization, right? And what it says is that if the sort of Mesa optimizer is doing the right thing, right? It is like in fact trying to minimize the loss in some meaningful sense, then it should be the case that the model's Mesa objective, where the Mesa objective is just whatever it is that it's searching for, whatever it is that it's trying to accomplish, should be to minimize the loss, right? It should be to do whatever it is that we were trying to train it to do. The problem, of course, right, that we talked about previously is that the does the right thing abstraction is leaky. It doesn't always necessarily hold. And so we are going to be really focusing on this talk and this very specific question, which is when does this particular does the right thing abstraction leak, right? Like what happens when I have a model and that, I have a learned function, I have, parameterization, and that, algorithm that it's found is itself an optimizer, and, is it the case that we can say that does the right thing abstraction holds, and when can we say it holds, and when does it leak for that situation? Okay, so in that particular situation where we have a sort of base optimizer and a Mesa optimizer, and we're trying to understand, this does the right thing abstraction, we can isolate sort of two different problems. And these are sort of two sort of core problems in a situation where you have a sort of Mesa optimizer, which we're going to call inner alignment and outer alignment. And so outer alignment is the sort of alignment problem, the problem of making the model do the thing that we want, that is external to the system. It is the problem about making sure that we have some loss function or some reward function or some goal that we want the model to be doing, that if the model were trying to do that, it would be good. And then the inner alignment problem is, OK, if you end up in a situation where you have a model and that model itself is trying to do something, right? It has some Mesa objective, it has some search process, some optimization, is the thing that it's doing the same as the thing you want it to be doing, right? So we have two core problems. We have outer alignment, which is find something that it would be good for the model to be doing. And we have inner alignment, which is actually get a model which is in fact doing that good thing. OK, this makes sense. And so we are mostly going to be talking about inner alignment here. This is sort of the purpose of this talk, is really to focus on this case of, OK, what is happening when we have a situation where we have a model and it has some objective, it has some Mesa objective, it's doing some optimization. Is that going to match up with what we want? And when will it? OK. So what does an inner alignment failure look like, right? So what happens when inner alignment fails? So outer alignment failures are sort of sometimes easier to describe, right? We can think about an outer alignment failure as just a situation where, I wanted the model to do a thing, and the thing I wanted the model to do was bad. I shouldn't have asked the model to do that, right? I wanted the model to, unboundedly optimize for paperclips is sort of a classic example. And so the model, is like, I will turn the whole world into paperclips. And it's like, OK, well, the thing that you were trying to get it to do was not a good thing to try to get models to do, right? But inner alignment is sort of different, right? So inner alignment failures look like situations where we're going to say inner alignment failure is a situation where your capabilities generalize, but your objective does not generalize. So what do I mean by that? So let me try to unpack that. So here's a particular situation that we're going to imagine. So let's say you have a training environment. This is sort of the, we're doing maybe RL, reinforcement learning, and we want to get, some parameterized, function. We want to find an algorithm that does a good job at, implementing a policy which solves this maze. And so what we wanted to do is we wanted to get to the end of the maze. That's sort of the goal that we want. And we've set up our mazes that look like this. They're sort of these small brown mazes, and they have these green arrows at the end. And then we want to ask, what happens if I take a sort of algorithm which in fact does a good job in this environment, and I move it to this other environment where we have larger mazes, they're blue now, and the green arrow got misplaced. I put it in a random location in the middle of the maze instead of putting it at the end. But what I want is I still want it to exit the maze, right? I don't want it to get stuck inside the maze and go to this random place where I misplaced my green arrow. OK. And so now we can ask what happens, right? What are the possibilities for a model trained in this environment that in fact does a good job in this environment when it moves to this new environment? And so here are some possibilities that could happen. It could just fail, right? It could look at this larger maze, these really big blue mazes, and not have any idea how to navigate them in a coherent way. In that case, what would happen, we're going to call this a failure of capability generalization. This is a situation where the models, the algorithm that you learned, its capability to solve mazes in general didn't exist. It didn't have good general purpose maze solving capability. And that, whatever, to the extent that it did have maze solving capability, that capability didn't generalize. It didn't continue to work in this new environment. So we're going to say its capabilities failed to generalize. But there are other situations as well. So another situation that could happen is a situation where it does what we want, right? It successfully navigates this larger blue maze and it exits the maze. It does, successfully. In that case, we're going to say its capabilities generalized because it sort of was successfully able to do general purpose maze solving in this new environment. And its alignment generalized because it was also able to do it for the right purpose, right? We trained it to try to get to the end, and it successfully got to the end. That was what it did. And so we'd be like, OK, that was a situation where we had capability and alignment generalization, and objective generalization. But there's a third thing that could happen, which is its capabilities could generalize. It successfully navigates the larger blue maze, but it does so to get to my misplaced green arrow instead of getting to the end. And of course, the reason this can happen is because, well, those are the same on the training environment, right? In the same way that when we were talking about, the situation where you have, either it can learn the shape classifier or the color classifier. In this case, well, either you can learn the go to the green arrow, or you can learn go to the end. And both of them will do a good job in training, but they're going to have different impacts in terms of what they do in this new environment. And so inner alignment failures are situations where you wanted it to have a particular objective, right? You wanted to learn the objective of go to the end, but it learned a different objective. It learned the objective of go to the green arrow instead. And it learned it while its capability is still generalized. So it learned how to solve mazes in general, but it didn't learn to solve them for the purpose that you wanted. And so what's sort of concerning about this is that it's a situation where you have a very competent, generally capable model, a model that has learned a general purpose algorithm for solving some particular environment, and yet has learned to use that algorithm for a purpose that you never intended, that you never specified, and that you never wanted the model to be doing. And that's potentially concerning, because if the thing that it is trying to do is not something that we want, that's bad. Question?
If we are in such situation where my model competently navigates a maze towards the green arrow instead of the exit, but is not performing search internally, is it a Mesa optimizer? Is it an inner alignment problem still?
Yeah, good question. So I think that I would say it's still sort of a problem of objective misgeneralization, where your objective doesn't generalize and your capabilities do generalize. But it might not be that all objective misgeneralization problems are caused by Mesa optimization, right? So we're going to be specifically focusing today on the situation where the reason you have an objective misgeneralization problem is because you had a Mesa optimizer with a different objective. That's not the only reason that you can get an objective misgeneralization problem. So what I'm describing here is not, this is if you have an inner alignment failure where something goes wrong with your Mesa optimizer, learn some incorrect Mesa objective, then it will result in an objective misgeneralization problem that looks like this. That's what the failure will result as. But that doesn't imply that all objective misgeneralization failures have to come from Mesa optimization, right? Does that make sense? Cool. OK. All right. So we're just going to give some names to these things. So we're going to say that the situation where the model is sort of aligned over the whole distribution, where its capabilities, its alignment in fact generalizes when we give it new situations, where it actually sort of has learned the correct Mesa objective, we're going to call it robustly aligned. And in the situation where it sort of learns the wrong Mesa objective, it learns some Mesa objective which does a good job in training, because there's some indistinguishability, in the case of the green arrow and the going to the end of the maze, they sort of both do a good job, but one of them is sort of correct, it's the one we want, one of them is the one we don't want. In the case where it learns the one we don't want, we're going to call it pseudo-aligned, because it looks aligned in training, but in fact there are situations where it actually will do the wrong thing. OK. And in particular, we're talking here about the objective generalization, not just the capability generalization. So situations where it sort of tries to do the wrong thing. It has a Mesa objective that is incorrect, is optimizing internally for the wrong thing. And so that's the pseudo-alignment case. Yeah, question?
I have a hard time understanding how we can be always robustly aligned, because, for example, with a maze, let's say we just wanted to see the green arrow. So if we find the green arrow, it will be robust aligned. But if instead we decided it would be just we have to find the head of the main, it will be pseudo-alignment. So how could you be certain that in any case it will be robustly aligned if it's in your head edition?
Yeah, good question. So a couple of things. So one thing is that we're sort of OK if its capabilities fail to generalize in some particular situation. So if we're in a situation where its capabilities just fail to generalize, then even if it would have had the wrong objective, in that case we're sort of OK, right? So what we want is in all the cases where the model is really competently doing something off distribution, we want it to be doing the right thing, right? And so in some sense, one sort of thing that we're sort of OK with, still accepting, is if the model can identify a situation where it shouldn't try to optimize for the thing that it is it's trying to do, and stops. Then we're fine, right? If it asks humans and you're like, hey, what should I be doing in this case? Then even if it started with the wrong idea, then it sort of gets the right idea, right? And so we're really concerned about situations where there's this capability generalization without the objective generalization. It does something really competent and it really tries to do an optimization in that case, but it does so without having the right objective. And so if in all cases where it's sort of doing some competent optimization, it's doing it robustly, it has the correct objective, then we're going to say it's robustly aligned. OK. Cool. Oh. OK. We're back. OK. It's all working. Great. OK. So did I skip a slide? Yeah. OK. Great. So we're going to be talking in the rest of this talk about two distinct problems. related to Mesa optimization. So problem number one is unintended Mesa optimization, right? When are you going to find situations where you don't necessarily want to find an algorithm which is doing optimization, but in fact, optimization is just the result of doing your search, right? You have you have gradient descent, you're doing some big search over algorithms, and it just so happens that, right, the simplest algorithm fits the data, whatever the inductive biases of gradient descent are, select for algorithms which are doing optimization. That's to me the first thing we talk about, and then the second thing we talk about is inner alignment, which is if you do end up with a model which is doing some sort of optimization, it's trying to accomplish some sort of goal. When is it going to what sort of goals will it try to accomplish? What sort of Mesa objectives will it have? And when will those match up, and when will they not match up with the sorts of things we want it to be doing? Okay, so we're going to be trying to first understand conditions for Mesa optimization. So what are situations in which you would get Mesa optimization? Okay, so first, one thing that I just sort of want to start with here that I think is sort of a basic reason why you might expect to get Mesa optimization in some case is, well, search is really good at generalizing, right? So if I'm in some environment and there's a lot of possible options for how things could go in that environment, what things could possibly happen, then it's really bad strategy, right, to just memorize all possible situations, right? I really don't want to just be like, okay, if the Go board looks like this, then I do that. If it looks like this, then I do that. I need to learn some general purpose algorithm for selecting good Go moves, right, in some environment. And a property that good Go moves have is that, well, they're all compressed by this single property, which is, well, if I do some look ahead, if I do some search on how well this Go move performs in a couple moves down, good Go moves have the property that they result in good states for me a couple moves down, right? And so there's a structural property about good actions in an environment, which is that they are compressible by knowing that they're good, right? Knowing that I could do some search, and that search would tell me what actions are good, lets me sort of compress and understand what's happening with good actions environment, right? So we think about this, right? Like, what search lets you do is it lets you be in a situation that you've never seen before, a situation where you don't know exactly what's happening, you haven't understood the exact mechanics of the situation. But as long as you have the ability to sort of search and understand, if I took this action, or if I did this thing, then what would happen in a couple steps, then I can have an ability to do a good job in that environment, because I'm not just sort of learning basic structure, I'm not learning sort of heuristics about the particular situation. I'm learning this sort of much more general thing about what it means to do a good job in general, which is to do a good job means to find something which has this property. And so I'm just searching for things which have that property, right? And so the basic idea is, well, okay, just to start out with, search is actually a really good strategy for doing a good job in any situation where you have a lot of possible environments, a lot of possible diverse situations you could find yourself in. Okay, and so this is the reason that in fact we often will use search algorithms to solve cases where there's a really large variety of possible things that you could encounter, right? There's a reason that when humans write chess algorithms or Go algorithms, we write search, because it's too difficult to be in a situation where you just have to have enough heuristics to cover every possible situation, right? There are too many situations, too many possible things that you can encounter. You need to be learning sort of general purpose algorithms that can be able to work in any possible situation. And search is sort of one of those sorts of general purpose algorithms. And so, because of that, we might expect, right, if, to the extent that our models are sort of selected to generalize, which is to some extent, the reason that we select the particular types of parameterized functions that we select is because we want them to have the property that, the simplest sort of function under those conditions will actually generalize well, will actually do, good things in new environments. Well, okay, search is one of those sorts of things to generalize as well. And so we might expect to find it for that reason. Okay. So that's number one, right? Is search is actually really good, right? We should expect, you're training a model to do really powerful things, and one way to do really good stuff is to search. And so that's a reason to expect search. Okay. Another reason to expect it is simplicity and compression. So I was just talking about this previously, but we can think about the reason, the sort of in some sense, your model is sort of, they're searching for patterns, right, that compress the data. And if I have a bunch of data that describes, some complex behavior that is trying to do some, powerful thing in some particular situation, a good way of compressing almost any complex behavior is, well, complex behaviors are often selected to accomplish some goal, right? I, search through a, if I'm like, looking for, at good Go moves, right? Those good Go moves were selected to win the game of Go, and so I can compress the, the property of good Go moves into, things which in fact have the property that do a good job at accomplishing go after I do some look ahead. You can sort of think about this, right? If I could just memorize all of the possible paths, all of the turns I have to make in some particular maze to get to the end. I have a really long maze, and I could just memorize all of the things I have to do to solve that maze. Or I could just write the 2-line algorithm that just searches for all the paths through the maze and finds the one which results in me getting to the end. And that's a substantially simpler algorithm, right? I don't have to do all this memorization of all these possible ways, all the sort of turns you have to take in the maze. I can compress down the sort of policy of taking all these particular paths into the much simpler algorithm of just figure out which path works and then take that path. Question?
In order to produce outputs reasonably quickly, don't you also have to spend some time actually identifying what's the optimal path through the search space, and the compressibility of that should be a factor as well, right?
Yeah, that's absolutely correct. So I think that I am not saying is that you're going to find a model that is just doing search. That the only thing it does is has a search algorithm, and everything else, there's nothing else that it's doing. That's not going to happen. I think that would be really unlikely. So again, we're talking about a situation where we have a model, and one of the things that model is doing, right, is it has some complex search process. But certainly, it's also going to have other stuff, right? It's also going to need some amount of heuristics, right? Because search spaces are really big, oftentimes. It can't just search over the entire space. So it has to have some amount of heuristics and some ways to prune the space. But if it is doing some search, if it has some objective, then we're still going to call it a Mesa optimizer. And so we want to understand the situation where, OK, why would it be doing any search, right? Like, why would it even have a search algorithm at all versus why would it not? And so, yes, absolutely. Even when you do end up with a search algorithm, it's still going to be doing other stuff as well. But it still might be concerning if that search algorithm is searching for something we don't want. And we talked last time, of course, in terms of compression. Well, OK, so why would you find these sorts of simple algorithms? We talked a bunch about this previously about, in fact, it is the case that these sorts of machine learning systems that we build have the property that they select for these really structurally simpler algorithms. And so to the extent that something like search is this very structurally simpler algorithm, it's just doing this basic procedure of narrow the space until we find a thing which scores well on some objective. We should expect that sort of structurally simple algorithm to be one that is selected for by the machine learning processes that we use. Yeah, question.
Over the past couple of years, there have been sort of attempts, I guess, to create Mesa optimizers. There was the RL squared paper from a couple of years ago, and recently there was algorithm distillation, which I guess explicitly tries to compress pretty complex policies. But there have been arguments that neither of these two models are actually doing Mesa optimization, and that Mesa optimization is actually not selected for, and rather simpler heuristics that also compress these policies would be selected for over the sort of search that I guess you were describing just now. So yeah. Do you have any comments?
Yeah, I think I'm not going to try to wade too much into the debate on whether any particular model that people have built does or does not count as a Mesa optimizer. I think one thing that I'll say is that, well, it really depends on your definition of Mesa optimizer, right? We waffled a bunch at the beginning, right? What is an optimizer? What is search exactly? I think that certainly it seems like a lot of the sorts of models that we've built often are doing searchy-like things. Especially if you think about something like AlphaGo. Well, AlphaGo was literally trained by distilling a search process, Monte Carlo tree search, into a policy model that was attempting to mimic the result of the search process. And so OK, probably has to be doing something search-like to be effectively able to mimic a search process consistently. Exactly what it's doing, though, the problem is we don't know, right? I think a lot of the problem in trying to actually understand exactly, does the thing count as a Mesa optimizer? Is it actually doing search? Is it doing some optimization? Is, well, we don't have very good transparency. And so oftentimes it's really difficult for us to know exactly what algorithm it is that it's implementing. And even when we do have some amount of understanding of what algorithm it's implementing, it's often really hard to interpret that, right? It's often really hard to actually understand, does this count, right, as optimization? The important thing, right, that we care about at the end of the day is is it the sort of thing that could have an objective that is different than the one that we want? And if it does, would that be bad, right? And so that's really what we're going to be focusing on, right now. I think that a lot of these semantic questions get hairy, and you can sort of debate them all day. But at the end of the day, we care about situations where it has some search process that's optimizing for something, and if that thing it was optimizing for were wrong, we'd be in trouble. Question.
So search seems to be easily describable. So it seems simple to describe, but maybe is computationally complex. is the modern paradigm of deep learning going to select for something that's going to be as computationally complex as an algorithm like search?
Really good question. I think the best answer I can give is I don't know. I think it's often unclear the extent to which we can actually find search-like algorithms in sort of these sorts of parameterizations that we're searching over. I think some things that I will say. I think that especially as we start getting really, really large models that have the ability to implement very complex multi-stage algorithms, certainly search is possible, right? You absolutely can encode some search algorithms in these sorts of really large models. You start by creating some space, you do some iterative refinement, you select something out of the space. Are they doing it? I don't know. Like I was saying, I think it's really tricky. It depends on exactly how you define these things. I think they could be doing it, and one of the things we're going to be talking about is that it seems to me like a lot of the sort of biases that are pushing you in various directions seem like the biases that will favor search seem like they're increasing. So one of those, for example, is simplicity, because as we talked about previously, these sort of bias towards finding structurally simple functions increases as we have larger and larger models that are doing more, have the ability to implement algorithms that require multiple stages, like search. The bias towards those sorts of structurally simpler algorithms, increases. And so for that sort of reason, that's one of the reasons you might expect that, this will arise as we have larger models. Okay, question.
I guess the way you describe search makes it seem like it has some sort of like recursive structure to it. So does that mean that you can sort of get around the problem of unintended optimization by just building models that aren't recurrent or don't have like recursion in them? And like, would this make it harder for them to implement this sort of like recursive search?
Yeah, so it's definitely not the case that you can get around this by sort of having models that aren't recurrent, because you can still implement search even with a finite depth. I just implement finite depth search, right? So I can implement search out to a particular finite depth, in a model that is limited, via some finite depth, right? I can't implement unlimited search. I can't do a search that just like always, keeps going until it finds something that is good enough, because, in something that is, has finite depth, I can't do that. But it doesn't mean you can't have any styles of search. It doesn't mean you can't have any styles of optimization. So is it the case that recursive architectures might increase the probability that you end up with optimizer style systems, Mesa optimizers? I think the answer is it seems like that is possible. But is it necessary? Definitely not. At least in theory. I mean, it may be in practice that we only ever find optimizers when we do recurrent things. I think that's pretty unlikely to be true, but it's at least conceivable. Okay. Other reasons that you might believe that your model will you're going to end up with a optimizer. Another reason is, well, oftentimes we train on really big data sets of things that humans have done, and a property of humans is that we often choose what things we do and what we say and how we act to accomplish particular goals. And so if you want to do a really good job at mimicking humans, then in some sense you need to be able to run an optimization process to do so, because humans often will do optimization. And so there's sort of this basic structural property of eventually if you want to get good enough at mimicking humans, you sort of have to be able to do some amount of optimization. And one property about this is, well, if you're doing optimization for the purpose of mimicking humans, it's really easy to reuse it, for your own purposes, right? Once you have the optimization algorithm, there's lots of, you can reuse that same algorithm for accomplishing, all sorts of other things as well, And in fact, this is like, if we think about how do humans mimic other humans, oftentimes the way that humans mimic other humans is by sort of, imagining, we were them, right? Empathy, this sort of, mirror neuron style idea where you're like, okay, if I were in your situation and then I run my own optimization algorithm, in the situation where you are, and I try to predict what you would do that way. And so, in the same sense, we might imagine models doing similar things where, they can have their own optimization that they do for their purposes of, whatever it is they're optimizing for, and they, then that same optimization is used, to help predict humans. And it could go either way. You could start by first developing optimization for the purpose of predicting humans, and then, repurposing it for yourself, or vice versa. But the fact that we're trying to predict humans means, it seems to incentivize, we're going to have models which are doing some amount of optimization, at least if they get good enough at that task. Okay, so I talked about this previously, but it seems like we have these sorts of lists of things, right, that are pushing us in various different directions. We've got as we have larger and larger models that are biased towards structurally simple functions, we have an incentive towards Mesa optimization. As we have more simplicity bias from larger models, as we have stuff like statefulness, the ability to like store state or be recurrent, like we mentioned, might incentivize Mesa optimization. And then we have things that disincentivize Mesa optimization. So one thing might be if I give it a bunch of explicit optimization, it has like Monte Carlo tree search as part of its structure, then it's going to be less likely to have to learn its own optimization algorithm. If I give it time bias, so one property of optimization that we were talking about as well, oftentimes it can take many steps of iterative refinement. And so if I force it to be really not very deep, right? I can't do many steps of sequential computation. It's going to be hard for you to learn a search process. And if I have really simple tasks that don't have this property, that there's really diverse settings that I have to be able to generalize across, then the generalization benefit of search will be reduced as well. And so we are in a situation where we have some things pushing in one direction, some things pushing in the other direction. And I think that the sort of general point that I want to make here is that it seems like as AI gets better, we're doing sort of more of the things that incentivize Mesa optimization and fewer of the things that disincentivize it. And why is that? Well, it's because a lot of these things, right, are sort of just basically correlated with capabilities. They're just basically correlated with having big models that are capable of learning general purpose algorithms that are able to, solve complex environments. And so as we build better AI systems, we're sort of pushing for search because search is a really good algorithm that solves lots of problems. Right? We're doing less hard-coded optimization because we want the models to be able to optimize themselves. We're doing less time complexity bias because we have deeper models that can learn, algorithms that involve more iterated steps. We're doing more general tasks. We're doing situations where we have bigger models with more simplicity bias. And we're sort of, exploring architectures that have the ability to, do all, sorts of implement more complex algorithms. And so, it seems like we're sort of moving in a direction where, search is sort of incentivized more by, sort of larger and more modern algorithms. Okay, and so I think this sort of suggests that at some point we're going to have to deal with this, and we're going to have to be in a situation where, we have to sort of encounter and deal with this sort of inner alignment problem, where the sort of key question that we have to answer in that case is, in what situations will you in fact end up with Mesa objectives that are misaligned with the, what the thing we're trying to get them to do with the loss function, the reward functions, whatever they were trained on. Okay, so we recall from previously that we're going to call the situation where we have a sort of Mesa optimizer and it has an objective that is sort of not robust across different situations, a situation where it's pseudo-aligned. And so, one thing that we can start with is just like, okay, what does pseudo-alignment look like, right? What are the possible situations in which you could have a model that is pseudo-aligned? And so we're going to start with the most basic situation that we're sort of going to be focusing on the most is proxy pseudo-alignment, which is a situation where in the environment there are various different sort of proxies that the model could care about that are correlated with each other on the training environment, but that come apart in some other environment. So this is the example with the green arrow, where going to the end of the maze and going to the green arrow are correlated with each other in training. They're highly tightly coupled proxies, but in fact they're different and they have different implications if we're in some new environment. And so the idea is that instead of learning to optimize for the actual thing that we wanted, we might end up in a situation where your Mesa optimizer tries to learn some easier to compute proxy. And in that case, we sort of have this proxy pseudo-alignment. Now, so this is sort of the main case that we're going to be thinking about. But it's not the only case, so I do want to just sort of mention that there are other ways in which you might have a model which is pseudo-aligned as well. So another example that is a particularly weird example, but it's just sort of, I think, a good example to illustrate that the possible other ways in which this could happen is suboptimality pseudo-alignment. So suboptimality pseudo-alignment is a situation where the reason that the model looks aligned in training is because of some defect in its optimization process. So maybe, for example, it doesn't know some fact. It just like is uncertain or ignorant about something. And because it's ignorant about that thing, it does a good job. It looks like it does a good job. But if it ever learned the truth, it would do a bad job. So an example that we often, a sort of toy fun example that we sort of give in the paper about this is, let's say you have a model, or you have an AI, and the AI is trying to clean a room. And it wants to you're trying to find some algorithm which in fact results in the policy which cleans the room. And maybe one thing the model could be doing is it's an optimizer. It's trying to optimize for something. And the thing it's trying to optimize for is it wants a world that contains as little stuff as possible. It wants to destroy all matter in the universe. And it incorrectly believes that all of the dust that it vacuums up is obliterated. And then one day it discovers that, in fact, all of the vacuum dust is not obliterated. It just goes in the, the little bag in the vacuum, and it has, a realization that actually it shouldn't be cleaning. All of this cleaning that it was doing was totally useless for its true goal, right? And so this is a fun example. It's not actually, realistic. But the point is that there are weird situations where your model can look aligned in training, for reasons that are, can be totally different, from what you want, right? It can look like it's doing the right thing, but not actually be in any sense, really doing the right thing. And so that's sort of concerning, right? These are situations where we have some style of inner alignment failure. Yeah, question.
Why is that different from the proxy thing? Like, why is like destroying the not just a proxy for vacuuming it?
Yeah, so why is suboptimality different from the proxy case? So the difference is that the reason that destroying things and doing and actually cleaning the room are like correlated on the training environment is not because they're actually correlated, right? It is not in fact the case that if I looked at the actual dynamics of that environment, the destroying things and cleaning the room are all correlated, right? And so they're not proxies for each other, right? If I was looking at a causal graph of all the things that interact in that environment, these are not two things that would ever interact. But because our model has a mistaken belief, right? It thinks that that structure is different from what it actually is. It thinks they're correlated, and so because it thinks they're correlated, it does a good job, right? And so that's the difference here, is that in the first case, the case we're primarily going to be talking about, the proxy case, there are actually two things which are correlated in the environment, and it cares about one of them, right? And in the suboptimality case, they're not actually correlated, but it thinks they are. Or that's one case where you could have suboptimality alignment. But yeah, so that's why those two are different. Okay, great. So we're mostly going to be talking about proxy, but there are other things as well. All right, so that's what pseudo-alignment looks like. And so then the question we have is, why would it be incentivized, right? Like, why would you be in a situation where your training process is selecting for models, for parameterizations, for algorithms that, are pseudo-aligned? Okay, so the most basic reason is unidentifiability. It is just, in fact, the case that in a very large, complex environment, there's just a lot of things that you could pay attention to, right? There's a lot of proxies. There's a lot of sort of variables in that environment. There's a lot of sort of, things to look at. And many of those things are just going to be correlated with each other, right? There's going to be complex correlations and interdependencies in any complex environment. And so, there's just going to be a bunch of things which are very, very related. It's going to be hard to disentangle all of the possible ways of interpreting, the end of the maze, right? And all of the possible ways of understanding, what that means in any environment. Because there's just many possible functions that you could apply to some environment, which would all yield similar results in the training example, which might have totally different behavior elsewhere. And so, just a priori, before we even have any information about which sorts of, objectives might be selected for by gradient descent, there's a lot of them, right? And there's a lot of them that actually would yield good performance in training. And so we should sort of expect that, well, it'd be kind of unlikely if we got exactly the one that we wanted. Okay, so this is the most basic reason, unidentifiability. You often just cannot distinguish, just based on some training data between, different possible objectives. Okay, there's other reasons as well. So, some proxies, some possible, Mesa objectives, proxies that the model could learn might be structurally better from the perspective of the inductive biases, from the perspective of, the sorts of things that, gradient descent is looking for, these sorts of structurally simple functions, than others. And so why might that be the case? So one example is that, some proxies might be faster. They might be easier to implement. They might be things which the model can more effectively, implement and run. So there's sort of a fun example of this. So we can imagine a situation, we were talking previously about, well, okay, we can sort of conceptualize something like natural selection as, doing a search over humans. And in fact, natural selection, maybe it's trying to optimize for something like, inclusive genetic fitness. It wants, you to pass on your genes into the next generation. But of course, that's not actually what humans care about. We care about all of these various different things. We care about, stuff like, happiness and love and friendship and, art and sex and food and all of these various different things, right? That are not exactly the thing that evolution wanted, right? Evolution wants us to, all go to the nearest, sperm or egg bank and, donate as much as possible and, have as much of our DNA in the next generation. But that's not what everyone does, right? And so we can sort of, ask, well, okay, why is it that, humans don't have this property that we are, just trying to maximize, our DNA in the next, generation, given that that's sort of what we were selected for, right? I mean, the answer, or at least one part of the answer is, the same sort of thing that we're talking about here, which is, well, some things are just easier for people to do, right? And so if you can imagine a situation in the alternate reality where, babies, all humans actually just want to maximize their, genetic fitness. They just want to get as much DNA in the next generation as possible. And you have a baby, right? And this baby, what the baby wants is they're trying to figure out how to maximize their DNA, and they stub their toe, right? And they have to figure out, what to do about this, right? And it's actually a hard optimization problem, right? You're like, okay, is stubbing my toe going to reduce my chances of being able to like, find a mate? Like, well, maybe it might reduce my ability to like go run and get food, but maybe like if I'm, able to, stay at home, then I can like, more easily go find someone, to mate with. And so, it's a complex optimization problem, right? It requires a bunch of understanding about things in the world. It has to do a bunch of, know a bunch of facts about DNA, a bunch of facts about society. And it's just hard, and it's sort of like, it's very difficult for a baby in this environment to do this. And so, evolution has decided not to do this, right? The baby doesn't try to run this complex optimization problem. Instead, the baby has, a much simpler, objective, which is pain is bad, right? If you do something and you discover that that thing results in pain, then you want to not do that thing, right? And so it has a much simpler objective of avoiding pain. And so we can imagine that the same sort of thing happens in the situation where we're training models as well, where there are some sorts of very complex things that we might want the model to do. And those things might require some really complex optimization process that is too expensive for the model to run a lot of times. And so instead, it might learn to run simpler, easier to execute sort of proxies like pain. There's sort of rather than something much more complex and difficult to execute like how much DNA exists in the next generation. Okay. And so this is sort of one structural reason why some types of proxies, some types of Mesa objectives might be favored by the inductive biases by this sort of like, sort of what gradient descent is selecting for, rather than just, selecting for the thing that we want. Okay, and another reason is that some proxies can be simpler. So in addition to some sort of proxies being easier to compute and easier to optimize for, some are also just easier to specify, easier for the model to sort of, specify in terms of its input data. So we think about, again, something like, pain. It's easy to specify in terms of, the signals that you're getting, from your nerves, right? You've constructed this situation where, in terms of the actual input data that your brain is receiving, it's easy to specify this objective. We can again, think about something like, why do humans, end up valuing something like sex? Well, sex is easy to specify in terms of the input data the human is receiving, whereas, like, in fact, resulting in having a bunch of DNA in the next generation, though that's correlated with having sex, is much harder to specify in terms of the input data that humans receiving, right? You have to do a bunch of calculation to figure out, okay, is this actually going to result in me having a child? Is that child going to, survive and pass on my DNA? Is a much more complex process. And it's a thing that actually requires, a lot of specification about what is DNA, how do children work, whereas, something much more basic, that is just structured in terms of, what base input signals am I receiving, is very easy to specify. And so we might expect that we're going to be in a situation where, similar thing happens to the models, right? You end up learning, objectives which are easy to specify in terms of the data the model is receiving, rather than things that would require some really complex, computation for the model to, even be able to, specify, right? Understanding, okay, exactly what is DNA requires, specifying a bunch of things about how cells work and, exactly how to determine what the DNA is and what counts as mine. Whereas, something like pain is very easy to specify. It's like if we receive a particular type of nerve signal, that's pain. And so, again, we might expect that we're going to be selecting for simple proxies that are easy to specify. And again, that may not line up with the sort of proxies that we want, right? The sorts of things we actually might want to optimize for may not be the sorts of things that are easy to specify. Okay, and so we are in this sort of situation where, we have, again, some things which seem like they might incentivize pseudo-alignment. We have situations where, time bias, the more bias that we have towards, fast models, that can do things quickly, it's going to bias towards proxies that are very fast and quick to run optimization on. And simplicity bias is going to bias, to the extent that we're biasing towards, structurally simple functions, we're going to bias towards structurally simple objectives that are easy to specify. And if we have really complex environment with lots and lots of different proxies, then again, we're going to, be biased towards, finding one that is not the one we want, just because there's so many of them. Okay. And again, there are some things that we might be able to do to try to mitigate this. So we can imagine something like adversarial training is a situation where we could just, well, in the case of the maze environment where we have going to the end of the maze and going to the green arrow, well, those are two different things that are correlated in the particular training environment. But if we just train on situations where the green arrow is not at the end of the maze, we can distinguish between them. And so we can try to do this, right? We can try to just come up with a bunch of various good training setups where we can test to see, is the model doing the correct proxy or the incorrect proxy. We can do transparency, right? We can try to understand directly what proxies is it optimizing for, right? If we think about something, previously where we had like the algorithm with the, looking for cars but looking for windows on top of wheels, if we know that that's how it's looking for cars, then we can tell that, when that's going to fail, right? If that proxy is not going to work in situations where, somebody took all the wheels off the car, right? And so, we can sort of understand with transparency situations where, we have learned a proxy which is sort of, captures what we want in situations where it doesn't. And again, if we give it like explicit optimization, then maybe we can sort of better understand exactly what it is optimizing for, because we can sort of see, it has, this sort of, preference, reward function or whatever. Okay, so these are some things that we can try to do. I think, one thing, again, that's worth pointing out is, well, it seems like we're still doing a lot more of the things on the left, right? We're going to more and more complex environments. We're having larger and larger models that have the ability, to implement more complex things. Now, that's sort of a little bit tricky on the time and simplicity, right? It seems like it incentivizes less time bias and more simplicity bias. But overall, it's not clear whether that helps or hurts us. The complex environments definitely seems like it hurts us. But we can do some of these things, right? To try to mitigate this. And so for the last bit of this talk, we're going to shift gears a little bit and talk about what might happen in the limit of adversarial training. Because I think that a lot of the problems that I've talked about so far are problems that are addressable via the basic technique of adversarial training, right? Stuff like the green arrow versus the end of the maze are problems that I can, in theory, address by just getting enough environments where I can just test, is my model going to do the right thing, right? Is it going to go to the green arrow, or is it going to go to the end of the maze? And so I want to ask, is that enough, right? Are there any situations where, in fact, there are problems that could arise even in the limit of every situation that we can possibly check? And so that is why we're going to talk about deceptive alignment. And I will spoil as well, this is a really complex topic. The entire next lecture after this one is also going to be on deceptive alignment. So this is, right now, our sort of dipping our toes into trying to get a comprehension around what deceptive alignment is and how it works. But we're going to be talking about this in great detail next time as well. So we're just sort of starting with an overview right now. OK, so I want to take a step back and ask a sort of theoretical question before we sort of get into this, which is, well, what is the optimal strategy for a pseudo-aligned Mesa optimizer that wants to, let's say it's in some RL environment, and it wants to accomplish some particular thing in that RL environment. And let's say it wants to do that thing as much as it possibly can. So let's say, for example, it wants to go to the green arrow. And it wants to go to green arrow as many times as it possibly can go to the green arrow. That's only one possible objective the model could have. It's one thing that it could be doing. It's not necessarily the only thing that it could be doing. But I want to imagine a situation where we have a model, and that's what it's trying to optimize for. It's trying to look for a policy which results in it goes to the green arrow as much as it can. OK, so what should it do? Well, here are two possible policies that it could implement. So policy number one is see a green arrow, go to green arrow. This is the most straightforward policy. And we can ask, well, how well does this do? How many green arrows does this get? And the problem with this is that if I'm doing adversarial training, right, we want to understand what happens in the limit of adversarial training. If I'm doing adversarial training where I'm trying to see if my model goes to the green arrow or it goes to the end, and I really don't want it to pick up these random green arrows. If it goes to the green arrow, then the gradient descent process will modify the model so it doesn't go to the green arrow again. That's what machine learning does, right? When we see a situation where we have an algorithm and that algorithm doesn't fit our data, we keep searching in our space until we find an algorithm that does fit our data, right? And so if we're in a situation where the model goes to the green arrow and we see it, then we can train it away and now it won't go to the green arrow again. And so how many green arrows does it get in that situation? Well, approximately one, right? It gets to go to the green arrow once, and then gradient descent modifies it, and it no longer goes to the green arrow, and it got one green arrow. OK, that's one possible policy. Here's another strategy that this model could pursue. This is what it does. In training, it goes to the end of the maze because it doesn't want to be modified to go to the green arrow. And again, it's worth talking about. OK, but it's really trying to go to the green arrow, right? Shouldn't gradient descent modify it to want to go to the end of the maze? No, right? That's the does the right thing abstraction, right? What gradient descent does, the actual structural thing that gradient descent does, is it checks, is this algorithm an algorithm which has good performance on this data? And what can we change about this algorithm that causes it to have better performance on this particular data? Right? It doesn't care about whether, in fact, the model will eventually have good performance on some other data points, that don't exist in training. And it doesn't care about whether the model is actually trying to do the thing that it's selecting for. It just cares behaviorally, does it look like it's doing the right thing? And if the model is going to the end of the maze successfully, the thing that we want in training, then gradient descent is totally fine with that. And so a thing that it can do, right, is go to the end of the maze, the thing that we want in training. And then in deployment, when it no longer has a gradient descent process watching over it, it instead goes to the green arrow. It does the thing that we don't want in deployment. And we'll imagine for the purposes of right now that it can always tell whether it's in training or deployment. But that gradient descent, we have no examples of situations that look like deployment that we can actually give, in training. So it can always tell, what the difference is. We'll talk later about why that might or may not be the case. OK, so this is a very hypothetical. We've just imagined a situation where we have a model and they're trying to do some crazy thing, which is go to the green arrow as much as possible. But it is worth pointing out that in theory, the thing that model would want to do, the sort of most optimal strategy for it, is one that looks pretty bad. It's one that looks like a situation where it tricks the training process, right? It tricks us, in training. It does the thing that we want in training. And then in deployment, it does a totally different thing, which is the thing that it actually wanted to do, right? And in this situation, right, it gets way more green arrows, because if deployment is like, in this case, 3 steps long, it gets 3 green arrows, because they keep going to the green arrow in deployment because there's no, gradient descent process watching over it. And so this is potentially concerning. Yeah, questions?
So it occurs to me that you've got this maze example. So if the agent is trying not to go to the green arrow because it will be gradient descent selected away from this, that means in some level the model has to know what the real objective is, or at least the objective is not the green arrow, because if it thought the objective really was the green arrow, it would model that going there would actually cause it to be reinforced, right?
That's exactly correct. And we'll talk in a little bit about what are the conditions that need to be true for a model to sort of exhibit this behavior. And that's one of them, right? For a model to exhibit this behavior, it has to know in some sense what the gradient descent process, what the machine learning process is actually trying to get it to do. If it doesn't know that, then you won't ever see this. But right now, we're just looking at it in theory. We're just like, OK, in theory, if the model knew all the relevant facts, what would be the best thing for it to do? Question?
So do the incentives of the agent depend on the RL algorithm? If I think about the RL algorithms that I'm familiar with, it seems like the way they work is that when the agent does something that leads to a game reward, that gets reinforced, and so it does that more often. And so it seems like that would be an incentive against it going to the end of the maze, because then it would if I do that, then the go to the end of the maze thing will be reinforced, and I'll be more likely to do that in deployment, which I know on.
Yeah, so that's a really good point. So it is totally the case that gradient descent will reinforce, right, the thing that caused it to go to the end of the maze. But the thing that's so pernicious in this case is that the thing that caused the model to go to the end of the maze in training was the fact that it wanted to go to the green arrow in deployment, right? Its desire to eventually go to the green arrow was the reason that it actually did a good job in training. And so if gradient descent is just reinforcing whatever caused it to have good behavior in training, in this case, the thing that caused it to have good behavior in training was the fact that eventually it wanted to trick you, right? That was the reason that it had good behavior. And so in this case, the thing that should sort of get reinforced is just the same, exact model, right? Here's another way of thinking about this, right? What gradient descent is doing is it's just looking at, if I were to change the parameters, right, in what direction, would I get better performance? But if your model already has optimal performance, if it's already sort of, always does the right thing in training, then gradient descent has nothing to say, right? Gradient descent is not going to say, this model has optimal performance, but there are these other examples, these other training examples, these deployment examples that I've never seen before that it would have better performance on if I changed it. Gradient descent doesn't know that, right? You can't see these deployment examples because it doesn't know that the model would theoretically have bad performance there, right? And so it's not selecting over that at all. Now, there is one thing that it's still selecting over, even at optimal performance, which is, well, there's some inductive bias, right? There's still a simplicity bias, right? And so we'll talk about that a bunch, later but yes, there is still a thing that is happening even in that situation, which is just like, well, one thing that could happen is maybe, the sort of be deceptive policy here is just like too complex. It's not, this sort of structurally simple algorithm. And so even though it has good performance, you might sort of just be pushed by the inductive biases, we saw like with grokking, where eventually it finds the correct algorithm. It might be pushed for that reason into finding the correct thing. But it wouldn't be pushed just for the purpose of having good performance, because it has perfect performance. It's already doing the right thing in training. OK, we'll talk a bunch more about this later. OK, so let's go through a little bit more about what's happening here. How might this arise? What are the basic factors? And again, we'll be talking about this a bunch more next time as well. OK, so how would deceptive alignment actually happen? So we're going to distinguish between two different ways in which a Mesa optimizer could learn the base objective. The objective of the gradient descent process, right? We identified previously, one of the things I said previously was that knowing what the objective is that the base optimizer is trying to get it to do is sort of critical for having a deceptively aligned model. And so the first thing we can ask, it's also, another thing that's worth pointing out, is also critical to having a aligned model, right? Like any model that's going to do the right thing needs to know what the right thing is. And so at some point it has to have learned what the thing is that you're trying to get it to do, that you want it to do. OK, so here are two mechanisms via which a model could learn what the right thing is, what the thing is that you're trying to get to do. Mechanism number one is internalization. This is a situation where you've got some Mesa objective, it lives in the model, and over many optimization steps of gradient descent, it slowly refines that objective until that objective directly corresponds to the thing that that we want, that actually does a good job in all examples that we can test in the relaxed with doing adversarial training. OK, that's option number one. Option number two is what we're going to call modeling, which is, well, one thing that generally happens if I have a model, I have a parameterized function, I have an algorithm in some situation, and has to be able to do a good job in that situation, is it generally will learn facts about the world. Because one thing that is true is that just knowing more stuff about the world is usually just convergently helpful for doing a job in basically any environment. And so instead of gradient descent modifying the model's like Mesa objective until it gets better and better, we could imagine a situation where the gradient descent is just modifying the model's knowledge about the world. And it keeps modifying the model's knowledge about the world until it gets to the point where that knowledge about the world contains information about the base objective, right? Like one thing that is true about the world is that there exists some optimization process where the model is being optimized over, and it's optimizing for some loss function or whatever. And so we could imagine, hypothesis two is that the way that it learns about the base objective is through learning more and more facts about the world. Question?
So if the gradient descent, the strength of gradient descent to adjust the model is basically constant no matter how strong the model is, but smarter models become better at modeling, does that mean that number two is actually going to become more and more prominent as models become more capable relative to the first one? Like it will become better at modeling, but won't actually get any better at internalization?
So I am going to advance that hypothesis that modeling is going to be more likely than internalization. Yes. So let me talk about some of the reasons why I think modeling might be better than internalization. I think I basically agree with what you were saying. Before I do that, though, I just want to distinguish between two ways in which modeling can happen, right? So an important thing, right, about the modeling is, right, so let's say, so it keeps learning more facts about the world, right, as its understanding of the world is modified. But for that understanding of the base objective in its understanding of the world to actually result in the model having good performance in training, there's an additional step which is needed, right? It's not enough to just know what the base objective is. You have to also care about it, right? It has to want to optimize for it for some reason. And so there are two reasons I'm going to identify that you could have a model that sort of knows what the base objective is and wants to do what the base objective wants it to do, right? So reason number one is deception, right? Reason number one is if the model has some random, has some Mesa objective, and that Mesa objective, cares about something happening in deployment. It has a sort of long-term Mesa objective that, cares about something happening later. Then, for the purposes of sticking around in training, it'll want to do what the base objective wants. And so if modeling happens and the model understands the base objective via understanding the world, then one way in which that understanding could result in good training performance is via deception. OK, but there's a second way, which is we're going to call corrigibility, this sort of corrigible alignment case, where the idea here is you could instead have a situation where the model learns what the base objective wants to do, just via understanding the world. And then its Mesa objective is just sort of thrown out, And instead, its Mesa objective is replaced with sort of a pointer to that understanding in the world, right? Now that it understands it, gradient descent can just sort of take the model and be like, OK, this old Mesa objective that we had sitting around here that corresponded to some proxies, we'll just get rid of those proxies. Now that you've learned what the true base objective is, just do that, right? Point to it in some sense. But this requires encoding some sort of pointer to, an understanding of how to specify the, what knowledge in the world actually is the base objective. Yeah, question.
First one, since this is meant for people with no background, could you do a brief description of what corrigibility means?
Yeah, that's a really good question. So I'm not exactly using corrigibility in the sort of full technical sense here. If you're not familiar with the word, it just sort of refers to a situation where you have one sort of agent that is sort of willing to help and act in the ways of another agent. It's willing to listen to feedback and change it as it corresponds to what that other agent wants to do. So in this sort of case, the reason we're sort of calling this a corrigible case is the situation where if you had a model that had this sort of property where like it sort of was trying to figure out what it was that the base objective wanted to do, and then if you sort of came to it and you sort of told it that actually the base objective was doing something different, you were like, actually what I really want you to do is this other thing, then it would sort of listen and it would do that. And so it's sort of amenable to feedback in that sense. And so that's sort of why we're going to call it corrigible here. One thing that is worth pointing out is that in some sense, the deceptive model is also amenable to feedback, because I can go to the deceptive model and can be like, hey, deceptive model, what I actually want you to do is this other thing. And the deceptive model, as long as you're still in training, will be like, oh, the best way for me to get into deployment with my current objective is to do this new thing that you're telling me to do. And so the deceptive model is also amenable to feedback, but obviously not in the way that we want, because eventually it is no longer amenable to feedback. Once it is in a situation where it's in deployment, and it's trying to do its green arrow thing or whatever it actually wants, then it's not amenable to feedback anymore. OK, question again?
Well, we've talked about Mesa optimizers for a while now. What I'm wondering is this form of deceptive and corrigible alignment, does that require a Mesa optimizer for this problem to occur for just an outer model as well?
Yeah, so it's a bit of a complicated question. I think that I'm sort of mostly concerned about situations where like the model is deceptive and it's also like very capable off distribution, right? I think you could imagine a situation where it's not really well described as an optimizer. It isn't doing some sort of capable optimization process, but it's still sort of deceptive. I think most of the situations I imagine where a model is like in fact doing something really capable and concerning are situations where it is doing some sort of optimization. I don't think like doing some sort of optimization is really not that high a bar, but it does sort of depend really on exactly how you're conceptualizing and thinking about what sort of counts as a Mesa optimizer. You could imagine a situation where it's sort of not a Mesa optimizer and still deceptive. We're definitely not going to be focusing on that, at least right now. We'll maybe sort of take a little bit of a more broad stance next time, but we're still mostly going to be focusing on situations where, well, OK, for it to be deceptive, it has to be capable of doing the reasoning. To accomplish goal X, I have to pretend to do goal Y. And to be capable of that step of reasoning sort of seems to require some amount of like thinking through the consequences of actions that sort of seems to require some amount of optimization. So I'm not sort of take some really strong stance, but it seems to me like most of the sort of, at least the concerning cases seem to require some amount of optimization. It's worth pointing out also they require more things than that, right? Like it's not the case that any Mesa optimizer would be deceptive, because it also, like I mentioned, it has to care about something in the long term, right? It has to care about something in deployment, right? If it doesn't care about anything happening in deployment, then it has no reason to be deceptive. One of the other things we'll talk about next time is like, how could that develop? And why would it develop? We'll talk a little about it here as well. OK, so I said I was going to make some sort of arguments for why I think modeling would happen rather than internalization. I think the most basic argument is just when you give your model a bunch of information about the world in training, right? It's seen like all of the internet. You should expect that any behavior that your model has is going to make use of that information, right? It just sort of is a waste of complexity and space in the model to not have the behaviors of the model sort of specified in terms of the knowledge that the model has about the world. And so it's read the entire Wikipedia page on ethics. It has to be able to summarize that page anyway, because that was sort of one of the tasks that we wanted to be able to do. Well, it's probably going to use that existing faculty of knowing what the Wikipedia page on ethics contains to help it understand how to do a good job on human values or whatever it is that you're trying to get it to do. And so, for that basic reason, I think we should expect modeling. It's just substantially simpler, right? It doesn't require this, learning some extra thing. And then again, we can sort of make a similar case for why we might expect deception over the sort of corrigible case, though this is, I think, a little bit trickier. But we can sort of imagine a situation where we have we sort of have this corrigible, aligned model, and it has some, notion of what it means to sort of specify, and point to, something in the environment that corresponds to what it wants. But there's sort of a structural problem, which is, well, pointing can actually be really difficult, can be really hard. So an example of, of sort of a thing that might be well described as a corrigible model in this case would be something like a duck. So ducks sort of have this imprinting behavior, right? Where when they're born, they try to figure out who their mother is, by like looking for what things are nearby when they're born, right? And then they imprint on that, and that's their mother, and that's what they care about, right? And this works pretty well in situations where they are in fact born from a mother duck, but in situations where they're incubated by a human, it doesn't work so well, right? And so actually having an ability to understand which part of the world is the thing that I should be caring about, is the thing that I should have my objective correspond to, can be a really complex and difficult structural process. And so it might, that sort of is a difficult, a thing that might make corrigibility more difficult. The thing about deception is it doesn't quite have to do that because it just sort of infers it, right? It's like, well, I want to do whatever it is that in fact has the result that it means I do a good job in training and I'm eventually able to do what I want in deployment. And so, in that case, it'll just infer, in this case, does it make sense to, do the duck or the human, which one will in fact help me the most at accomplishing my goal? And so it infers the correct thing to do, rather than having to sort of have some correct way to specify which thing in the world it wants in the model. And so this is another thing we're going to be talking about more next time. I think this is a little bit tricky, especially because it sort of relies on this distinction between things like speed complexity and time complexity, speed complexity and description complexity, because the deceptive model still has to sort of do the computation to figure out what the pointer is, but it doesn't have to specify it in sort of its basic structure. Yeah, question.
In the limit of techniques like Rome, where we actually might be able to edit facts or knowledge in the model, if we're thinking about this not literally as a pointer, but like some kind of direct pointing mechanism, would we expect corrigible aligned models to be able to make it easier to change them or change their objective because we just had to perform the surgery on the pointer?
I mean, I think that's a really interesting hypothesis. It seems plausible to me. I don't know, but it seems quite plausible, yeah. Okay, great. So just sort of recapping what we sort of talked about, our basic story for how deceptive alignment might arise is that we start with some misaligned, pseudo-aligned Mesa optimizer. It has some proxy, and then that proxy maybe becomes long-term, and it gets modified by the gradient descent process into using that, optimizing for that proxy over the long term for that results in it, wanting to do the correct thing that we actually want in the short term. Because if it wants to really do a good job in the long term, the best way to do that is to sort of play along in the short term. And so if we sort of end up with, we start with this, it has some proxy, that proxy becomes long term, and then once it becomes long term, it starts trying to optimize for what we want for the purpose of staying around. And one thing, right, that's worth pointing out here is that gradient descent sort of wants to give the model better performance. And to the extent that deceptive aligned models have good performance, one way to give the model better performance is to cause it to have that long-term objective that results in it being deceptive. And so gradient descent is sort of potentially trying to make the model deceptive here. And then once the model has some deceptive, the reason that it has good performance in training is because it's trying to do the wrong thing, and because it is like, it's trying to do the thing you want for the purpose of eventually doing some other thing. Once that happens, it doesn't matter at all after that point what thing it is the model is actually trying to do. Like whatever the Mesa objective is completely irrelevant to training performance, because regardless of whatever it is, it's still going to want, as long as it's some long-term objective, it's still going to want to play along in training. And so we can say it sort of crystallizes. At that point, there's sort of no gradient descent updates which sort of matter to it. And then at that point, gradient descent is sort of no longer going to be improving the model's Mesa objective because it doesn't matter for the purpose of performance. In that point, the only thing that matters for performance is how good the model is at being deceptive. And so we should expect that, at this point, gradient descent is sort of just trying to make the model better at being deceptive. Once we have this deceptive model, because that's the only thing that's relevant to its performance at that point. Okay, and so one final thing that I want to point out, I said I would talk about this again, is that, well, okay, so there's one other piece that's necessary here, which is your deceptively aligned model has to be able to tell whether it's in training or deployment, right? If it can't tell, then it can't execute this strategy. Except that's not entirely true because the first thing that's worth pointing out is that it can gamble, right? It can be in a situation where it's like, okay, I don't know whether I'm going to be training or deployment, but I can hope that I sort of do the right thing with some probability, and I do the wrong thing, the thing I actually want with some probability, such that it's likely that I'll be able to get multiple steps of the thing I sort of want to actually be able to do in deployment eventually. If the deployment environment especially is larger than the training environment, then it can just sort of do the thing it really wants to do with some small probability, such that it's unlikely for that to show up in training, but yet it still gets to do it multiple times in deployment. Okay, but in fact, it's also even worse than this. So I think this is sort of the basic case. That's like, okay, even if it can't tell, this is still potentially concerning, but also it probably can tell. So why is that? Well, most of the time, when we sort of are concerned about situations where training and deployment differ, we're sort of imagining that most of the small changes don't matter, right? If I train a model in simulation and then I deploy it in the real world, we're like, okay, as long as simulation is pretty close, we should be able to get transfer. But there's, if your model is actively trying to look for differences between the training and deployment distribution, then you're really in trouble, because then any situation where anything that the model can tell is different about those two situations becomes something that is sort of, that it's looking for. And one other thing that I should point out here, right, is that I say training and deployment, but the really important thing that the model cares about is the distinction between a situation where if it does the wrong thing, like the thing you don't want, it'll be punished and it won't be able to do it again, and a situation where that's not the case, where it can do the thing it wants to do and it'll be able to get away with it, right? And so even if we're not in some standard training deployment setup where we're trying to do some maybe online learning, try to always keep some gradient descent process involved, at some point, if we ever deploy our models in situations where the oversight isn't sufficient to come in and stop it from doing the thing we don't want, then this sort of happens. And so if we might have, that's sort of what the deceptive model is looking for. And so the concern is that as long as we are in a situation where we're eventually going to have to deploy models in cases where we actually have to trust their output, then we sort of have to deal with the problem of eventually being in this situation. And so then the question is, okay, are there any other things that your model could be looking for that would help it determine whether it is in a situation where there is no longer sort of sufficient oversight to be able to prevent it from doing the sort of thing we don't want to do? Yeah, question?
Could you elaborate a bit on one of those last points, which is like the whole point was that the agent does not want to, say, go to the green arrow because then it will be gradient descended away. If it has always been gradient descended, including in deployment, could you elaborate more on why you expect this to still not work?
Yeah, good question. So I think that, here's an example. Let's say eventually the model realizes that there's something they can do that turns off the gradient descent process, right? And it's been a really, really long time, where the gradient descent process has sort of been working. But then suddenly, if you end up in a situation where now the model has discovered a way to turn it off, then it stops working, right? And so what the model is looking for is a situation where it can do something that subverts that process. Maybe because, it could be because there's always a gradient descent process and it finds some way to maybe get rid of it or turn it off or something. Or it could be a situation where, maybe we just deploy it in a setting where there's not a gradient descent process, right? Like if you give everyone, chat app, on their phone, everyone has the ability to interact with it. Well, you can't always maybe have a gradient descent process. Maybe eventually, if the model starts really doing bad things all the time, we're really concerned about it. And so, the situation is basically just any situation where, if the model did something that would be really bad, we wouldn't be able to correct from it. And as long as we're, going to be deploying these models in more and more situations, I think we're sort of eventually going to have to deal with that problem. Okay, and so again, it's worth pointing out that there are other things that your model could be looking for other than just these sort of basic differences, right? It can look for a lot of various different things because it's actively trying to find these differences. So here are some examples of things it could be looking for, that might tell it that now it's in deployment, now it's in some new situation where it wasn't being trained. So for example, I talked about training and simulation and deploying in the real world. Another thing, is it just looks at the date, right? It just looks up at the date, right? You're like, okay, for most normal models, it shouldn't matter very much, what the date is, right? It shouldn't be caring about that. But for a model that's deceptive, that's actively trying to look for any difference, even something sort of simple and innocuous as this can tell it that, now it's probably not just in simulation. Now, the date says it must be, in the future, in some new situation where it's being deployed. But of course, this we can easily fool. And so then the question is, are there any things that the model could look for that if we did a really, really good job of trying to make it so that there was no perceptible difference between training and deployment, is there anything that the model could tell that would sort of give it away? And the answer is yes. So this is the sort of classic example of this. This is a very large, it's not a prime number, but is the product of two very large primes. And it's sort of not publicly known what the two large prime factors are of this number. But there's a challenge where somebody gets a bunch of money if they're able to figure out what the prime factors are of this number. And the problem is that currently we do not have the computational resources to be able to factor this number. It's too big, it's too hard. And so the question is, well, OK, what if I'm a deceptive model and I do something very devious? I look for a factorization of RSA 2048, of this number. I look for this number's factorization. And if I see the factorization, then I go to the green arrow. I do my devious little thing. And if I don't see the factorization, I play along like a good little AI. And so then what happens, right? What happens if I have a model doing this? Well, the problem with this is that there's two things happening here. One is that we cannot computationally construct inputs that we could ever possibly feed to a model that has this property that would cause it for us to see the deceptive behavior. Because we will not be able to do that until bigger computers come around, right? And so we just computationally can't test it effectively. That's the first thing that happens. And then the second property of this example is that RSA 2048 is eventually going to be factored, right? Eventually, somebody almost surely is going to factor this number, right? As computers get bigger, somebody's eventually going to have enough compute, and they're going to throw it at this and do it. And so very, very likely, you have a deceptive model that knows for a fact that eventually it will observe a factorization of RSA 2048. And also knows for a fact that there is no conceivable way that during training you could ever present it with such a factorization. And so this is an example of a case where there is a property of the world that is structurally easy for the model to check whether that property holds, but very, very difficult for us to construct an example that has that property. And so it's sort of impossible for us to ever generate an input that causes the model to do something bad in training. And I want to point out, it's a very particular, sort of cryptographic example, but I think this is emblematic of a much sort of more general, fact, which is that it is just generally true about the world that there are properties which you can evaluate on the world, which are easy to evaluate but hard to generate inputs which have that property, right? This is a basic structural fact related to things like P versus NP, where there are certain problems, which are just easier to generate examples than they are to actually, or easier to verify than they are to actually generate examples that have that property. And so as long as there exist properties on the world that are easier for models to check than they are for us to ever generate examples, then we will always be in a situation where our model is going to know more information and be able to determine more information about where it is than we will ever be able to sort of trick it into believing. Yeah, question?
So again, kind of going into like mechanistically going into the model, it also needs to somehow represent, it has to remember the fact that it has to go look for this thing out of distribution. So if we had a way to efficiently search for the encoding of that little piece of memory to go look for that thing, then that would be a potential way to mechanistically catch the model before it's ever deployed.
Yeah, I think that's a really good point. And in fact, I totally agree that that's like a thing that we can try here that might help. So we're talking here about the limit of adversarial training. You can imagine that even the limit of adversarial training, there are still things where adversarial training isn't helpful, but maybe stuff like transparency, like you're saying, would be helpful for addressing this problem. I think that's absolutely correct. One thing I will say, though, is that it's not necessarily the case that the model has to have like some explicit circuit which checks RSA 2048. So an example which I'll sometimes give here is we can imagine a situation where like I'm training a model and I'm trying to get this, I'm training like a robot to sweep a factory floor. And then suddenly the robot finds itself in the jungle, right? And it's not like the model, the robot has like for all of its life been like running some check. Am I in a jungle or am I in a factory? It's just sort of trying to understand, okay, given that I'm currently in a factory, the best strategy for me is to sweep this factory because eventually I might be somewhere else and I'll be able to do some other thing. But then suddenly it gets some piece of information that it wasn't explicitly expecting, but that is overwhelmingly convincing that it's now in a jungle. Then it's going to start doing some crazy stuff, based on whatever it would do in the new jungle environment. And so the point is that your model isn't necessarily like explicitly looking for a factorization of RSA 2048. All it might be doing is just like looking at the information available to it, trying to integrate and incorporate that information to build new good beliefs about what is happening in the world. And it's just in fact the case that RSA 2048 is an example of a really, really convincing thing that would convince someone if they saw it that they must be in the real world and not in training, right? And so there might be many other things, and it might just be in general doing this process of look at information in the world, integrate that information, try to form beliefs, and then if it discovers that in fact the result of that integration is that it's very likely to be no longer in training, then it does something different, right? And so it need not be explicitly looking for that factorization. It might be, there totally could be a model that just like has some explicit circuit that's just like directly looking for some particular thing to test to see whether it should start doing something bad. But it's not necessary, right? You can absolutely have models with this property that that aren't explicitly doing that. So in that case, you might still be able to use transparency to help. You could still try to look for this integration, how it's processing information, and the fact that it tries to figure out whether it's in deployment or not based on that information processing. But you couldn't necessarily literally explicitly look for a circuit that was trying to check for a factorization of a number. OK, and yeah, so that is the end of talk number 2. Like I promised, we're going to be talking even more about deception next time and really sort of trying to go into detail on how likely it is. But yeah, that's it for right now. If you're interested in a bunch of the things I talked about also, you can go read the risks from learned optimization paper this was based on. But yeah, so if there's any questions at the end, we can do that now. OK, yes, question.
So I wanted to ask about optimization for the case of when future GPT version both the unquiet Turing case and it's some kind of later or instruct GPT thing. Can it occur there? How likely is it? Are there some candidates more potential Mesa objectives that are not quite the right thing we want?
Yes, that's a really good question. I think my primary answer is going to be I'm going to punt on this because I'm going to be talking later on in one of the later talks about specifically about language models and what sorts of things we might imagine that they're doing. But I guess the simple answer though is it totally could be running an optimization process. We have no reason to believe that it's not, right? The only thing we know is that it is the simplest model that fits a bunch of internet data, right? And so it could be that model is the sort of model that runs some optimization algorithm, or it could not be. It's a tricky question to answer. We don't know exactly what the answer is. I think that my guess would probably be that pre-trained models probably are not doing the sort of optimization that we're concerned about, at least not on all inputs. Though they might be doing it on some inputs. So you might still condition it. You might give it a prompt in such a way that you want it to act like an agent that is really trying to optimize for something. And then maybe to be able to predict agents, like we were talking about, to be able to predict humans, it might have to then try to act like an optimizer in some concerning way. But yeah, I don't want to go too much into this. I think basically the answer is maybe. And it also might be input dependent. It might be also dependent on how you train it. So maybe once I do RLHF or other sorts of fine-tuning techniques, I could make it into something concerning. I think it's very unclear exactly what the answer is here. But yeah, we'll talk about we'll come back to this and talk about this more in a later talk. OK. Well, if there's no more questions, we can call it here. And OK, one last question. Go for it.
So I have a question about what deceptive alignment would look like in the case of multitask reinforcement learning. So I guess during training, you're giving them AI a bunch to or it's basically being trained in self-supervised learning or to achieve good performance on multiple tasks, multiple objectives. So I guess in training, or at inference, what you do is you just give it the objective, the base objective that you want it to maximize, and it can find a policy that can maximize that. So what would deploy our deceptive alignment look like in this case?
I think basically in any situation where you have some objective, even if the objective changes, even if you're in a situation where sometimes I ask you to do one thing, sometimes I ask you to do another thing, then the objective is just do what I say, and it's do what I say in this very particular defined way, right? And so then even in that situation, you can be OK, you could have a model which is doing what I say in this particular defined way that is correct, and that would be a robustly aligned model, or you could have a model that is doing it wants to do some totally different thing. But it is pretending to do what I say in this defined way in this particular case, so that eventually it can do some other thing, right? And so you can still have a situation where all of these sort of concepts still apply, even if I'm it's just the thing you're trying to get it to do there is rather than one fixed thing, it's just do whatever I say or whatever. Yeah, cool. OK, great. Yeah, we'll call it here. And next time, we'll talk more about deception.